Every time you pass by a railway track, you've walked over one of engineering's most ingenious secrets, countless carefully engineered stones that literally hold our transportation system together. These aren't random rocks scattered by nature. Every single stone has been precisely crushed, sized, and shaped according to strict specifications that most people never realize exist. What you're looking at underpins modern railroads worldwide and prevents derailments that would otherwise occur without this critical foundation. High-traffic railway lines replaced as ballast every 15 to 20 years to maintain safety standards, revealing just how essential these seemingly ordinary stones are to keeping trains running safely across the globe. The hidden science behind stone selection. But what exactly makes these stones so special isn't immediately obvious to the naked eye. Engineers spend years perfecting the exact specifications through a selection process that involves far more science than most people realize. Railway ballast stones must pass through rigorous testing protocols that would surprise anyone who thinks these are just ordinary rocks. Engineers examine every aspect of these materials, from their chemical composition to their physical properties, before approving them for railway use. Each stone must meet incredibly precise requirements for angularity, surface texture, and internal structure that determine whether a railway system succeeds or fails. The angularity measurement focuses on ensuring stones have multiple fractured faces rather than smooth surfaces. This requirement isn't arbitrary. Stones with insufficient fractured faces lack the mechanical interlocking properties essential for track stability. Surface texture requirements focus on roughness values measured using specialized equipment that evaluates how much friction each stone can generate when pressed against neighboring particles. The process begins in quarries, where geologists identify rock formations with specific mineral compositions and hardness ratings. Suitable ballast materials typically include granite, basalt, and quartzite, each offering different advantages for railway applications. Granite, with its interlocking crystal structure, provides excellent durability and resistance to weathering. Basalt offers superior resistance to freeze-thaw cycles that can damage track foundations in cold climates. Quartzite delivers exceptional hardness but requires more energy to crush into proper sizes. Geologists use core sampling to test rock formations at various depths, ensuring the entire quarry can produce consistent quality material. Different types of these materials are tested for their ability to withstand millions of compression cycles without breaking down into dust. Laboratory testing involves subjecting stone samples to repeated loading cycles that simulate decades of train traffic according to research protocols. The testing equipment applies loads at frequencies matching typical train passage rates. These materials must maintain structural integrity through millions of loading cycles, though their higher cost makes premium stones suitable mainly for heavy freight corridors where the investment justifies the performance benefits. The crushing process itself is an engineering marvel, using specialized machinery that creates the optimal angular shapes rather than rounded pebbles. Primary crushers break quarried rock into pieces roughly 150 to 200 millimeters in size. Secondary crushers reduce these chunks to the 50 to 75 millimeter range required for most railway applications. The crushing equipment uses impact and compression forces specifically designed to create fractured surfaces rather than smooth breaks. Jaw crushers apply slow, steady pressure that produces fewer fine particles. Impact crushers use high-speed hammers that create more angular fragments with better interlocking characteristics. Quality control laboratories test each batch using the Los Angeles abrasion test, which measures how much the stones will degrade under mechanical stress. This test involves placing stone samples in a rotating drum with steel spheres, then measuring material breakdown after standardized testing cycles. Quality ballast materials typically show low abrasion values, meaning minimal material degrades during testing. Premium ballast materials achieve even better performance ratings. Materials exceeding acceptable abrasion limits are considered unsuitable for mainline railway applications. Temperature resistance is crucial since these stones must maintain their integrity in climates ranging from Arctic conditions to desert heat. Thermal cycling tests expose stone samples to extreme temperature ranges through multiple heating and cooling cycles to simulate years of seasonal temperature variation. Stones that crack or spall during thermal cycling are rejected. Granite generally shows excellent thermal stability due to its uniform crystal structure. Basalt performs well in cold climates but can become brittle in extreme heat. Quartzite demonstrates superior thermal resistance across all temperature ranges. The grading system ensures that stone sizes follow precise mathematical distributions with specific percentages of different diameter ranges. Standard ballast grading requires careful controlled particle size distributions to maintain proper mechanical properties. The largest particles provide structural stability. Medium particles fill gaps and enhance interlocking. The absence of very small particles maintains proper drainage characteristics. This precise size distribution prevents segregation during transport and placement while optimizing mechanical properties. Even the surface texture is controlled through specialized crushing techniques that create the right amount of roughness for optimal interlocking. Crusher settings determine the amount of surface area created during the fracturing process. Higher crusher speeds generate more surface texture, but also produce more fine particles that can clog drainage systems. Lower speeds create smoother surfaces with reduced interlocking capability. Engineers adjust crusher parameters to achieve optimal surface roughness values. Surface texture measurements use laser scanning equipment that maps microscopic surface variations across representative stone samples. Production quality control extends beyond individual stone properties to batch consistency. Automated sampling systems collect representative samples throughout production cycles. Chemical analysis ensures consistency within acceptable ranges. Particle size analysis uses mechanical sieving to verify grading compliance. Shape analysis employs digital imaging systems that measure angularity and surface texture of thousands of particles per sample. Statistical process control tracks all parameters over time, triggering production adjustments when values drift outside specification limits. Specialized testing equipment evaluates additional properties that affect long-term performance. Petrographic analysis examines rock sections under microscopy to identify potentially harmful mineral phases. Some minerals can cause chemical degradation over time. Others can expand when wet and disrupt track geometry. Soundness testing simulates chemical weathering processes. Stones that show excessive degradation during soundness testing are rejected for railway applications. This scientific approach to stone selection reveals why railway ballast represents one of the most precisely engineered bulk materials on Earth. The specifications governing ballast production are more stringent than those for many construction materials. Every aspect of ballast stones, from their mineral composition to their surface texture, is controlled through rigorous testing and quality assurance programs. This level of precision explains why ballast stones look remarkably similar regardless of their geographic origin. They all must meet the same demanding engineering requirements. Yet the real engineering magic happens not in the individual stones themselves, but in how these carefully crafted pieces work together once they're placed on the track. The interlocking mystery that prevents disasters. The secret to railway stability lies in a phenomenon that engineers call mechanical interlocking, and it's more complex than most people realize. This interlocking system operates on principles that go far beyond simple friction between stones. When trains weighing thousands of tons travel at high speeds, the forces trying to push tracks out of alignment are enormous. The ballast stones must work together as a unified system to resist these forces, and mechanical interlocking provides the mechanism that makes this possible. When you look closely at ballast stones, you'll notice their jagged, angular surfaces aren't accidental. They're specifically designed to grab onto neighboring stones. These angular surfaces create contact points where stones physically hook together. Each contact point generates friction forces that resist movement in multiple directions. The jagged edges work like tiny mechanical fasteners, preventing stones from sliding past each other when subjected to external forces. Engineers design crushing equipment specifically to create these angular surfaces, rejecting any production methods that would create smoother, more rounded particles. This interlocking effect creates what engineers call a friction matrix, where each stone interlocks with its neighbors in a three-dimensional network. The friction matrix operates through direct contact between adjacent particles and extends throughout the entire ballast layer. When one stone experiences force, that force transfers to neighboring stones through the contact points. These neighboring stones then transfer forces to their neighbors, creating a network effect that distributes loads across thousands of individual particles. The three-dimensional nature of this network means that forces can be redirected in any direction needed to maintain stability. The angular coefficient, measured in degrees, determines how effectively stones resist lateral movement when subjected to dynamic loads from passing trains. Engineers measure angular coefficient by analyzing the shape of individual stones using digital imaging systems. Stones with angular coefficients above 150 degrees provide optimal interlocking performance. Lower angular coefficients indicate more rounded shapes that reduce interlocking effectiveness. The measurement process involves photographing stones from multiple angles and calculating the average angle between adjacent surfaces. Quality control systems continuously monitor angular coefficients during production to ensure specifications are met. Laboratory tests show that rounded river stones, despite being the same material, provide only 30% of the stability of properly crushed angular ballast. These comparative tests use specialized equipment that applies lateral forces to ballast samples while measuring displacement. River stone samples typically show lateral movement of 15 to 20 millimeters under standard test loads. Angular crushed stone samples show movement of only 4 to 6 millimeters under identical conditions. The dramatic difference demonstrates why railway specifications require crushed stone rather than naturally rounded alternatives, even when the source rock material is identical. The interlocking mechanism works through friction at contact points and micromovements within voids that distribute forces across thousands of contact points. Friction develops at every point where stones touch each other. The angular surfaces increase the contact area and create higher friction coefficients than smooth surfaces would provide. Mechanical interference occurs when the irregular shapes of stones prevent them from moving past each other. Load transfer happens when forces applied to one stone get transmitted to neighboring stones through the contact points. This combination creates a stable foundation that responds to loads as a unified structure rather than as individual particles. When trains apply lateral forces during cornering or braking, the interlocked stone matrix acts like a solid foundation that can resist movement. Cornering forces develop when trains navigate curves at speed. These forces try to push the outer rail and its supporting structure outward from the curve. Braking forces create longitudinal loads that attempt to push the entire track structure forward. The interlocked ballast matrix distributes these forces across wide areas, preventing localized failures that could lead to track misalignment. Emergency braking situations can generate forces exceeding normal operating loads by factors of 3 or more, making the interlocking system critical for safety. Computer simulations reveal that without proper interlocking, railway tracks would shift laterally by several centimeters after just a few train passages. Advanced finite element modeling simulates the behavior of ballast systems under various loading conditions. The simulations model individual stones as discrete elements with contact forces calculated at each interaction point. Results show that non-interlocking spherical particles allow track displacement of 40 to 60 millimeters after simulating 100 train passages. Properly interlocked angular particles limit displacement to less than 5 millimeters under identical conditions. These simulations help engineers optimize ballast specifications for different operational requirements. The ballast also dampens much of the wheel rail vibrations through energy dissipation at countless contact points throughout the stone matrix. When trains pass over tracks, they generate vibrations that would otherwise transfer directly to the ground and surrounding structures. The interlocked stone network absorbs these vibrations through friction and micromovements at contact points. Each contact point acts as a small energy dissipator, converting vibrational energy into heat through friction. The cumulative effect of thousands of these contact points creates significant vibration reduction that improves passenger comfort and reduces structural stress on nearby buildings. The breakdown of this interlocking system, often caused by stone wear or contamination, is responsible for many railway maintenance issues worldwide. Stone wear occurs gradually as repeated loading causes small particles to break off from contact points. These fine particles accumulate in void spaces between stones, reducing the ability of larger particles to interlock effectively. Contamination from external sources like vegetation, soil infiltration, or spillage from trains creates similar problems. Fine contamination acts like lubrication between stones, reducing friction and mechanical interference. Understanding this interlocking mystery explains why railway engineers are so particular about ballast specifications and why shortcuts in stone selections lead to catastrophic track failures. The mechanical interlocking system represents the foundation of railway safety and reliability. Without proper interlocking, trains would be unable to operate at current speeds and loads. Yet this sophisticated interlocking system is only the beginning of how ballast stones protect railway infrastructure. The real test comes when massive trains bearing thousands of tons roll over these carefully engineered foundations. Load distribution engineering marvel. When a 6,000-ton freight train thunders over railway tracks, the forces involved will crush most surfaces, but ballast stones perform an engineering miracle. The weight of these massive locomotives and their cargo creates pressures that would devastate concrete, asphalt, or virtually any other surface material. A single freight car loaded with iron ore can weigh 125 tons, and modern freight trains routinely pull 100 or more of these cars. The total weight pressing down on the rails reaches levels that would cause immediate structural failure in most construction materials. Yet ballast stones handle these enormous loads day after day, year after year, without catastrophic failure. The load distribution mechanism works through a principle called stress diffusion, where concentrated wheel loads spread outward through the stone matrix. Engineers use mathematical models to calculate how forces propagate through granular materials like ballast. The stress diffusion follows predictable patterns based on soil mechanics principles developed over decades of research. When a train wheel applies force to a rail, that force transfers through the rail to the sleeper below. The sleeper then applies that concentrated force to a relatively small area of ballast stones directly beneath it. These stones immediately begin distributing the load to neighboring stones through their contact points. Each railway sleeper concentrates the weight of an entire train car into a relatively small contact area, creating pressures that would exceed the bearing capacity of most soils. A typical concrete sleeper measures approximately 2.5 meters long and 0.3 meters wide, creating a contact area of roughly 0.75 square meters with the ballast below. When a 125-ton freight car passes overhead, this sleeper must transfer that entire weight through its small contact area. The resulting pressure can reach 15 to 20 tons per square meter directly beneath the sleeper. Natural soil can typically support only 2 to 5 tons per square meter before failing, making direct placement of sleepers on soil impossible for heavy railway operations. The ballast layer acts like a sophisticated load spreading system, taking point loads of up to 25 tons per square meter and distributing them across much larger areas. The load spreading occurs through the natural mechanics of granular materials under compression. As pressure applies to the top layer of stones, these stones compress slightly and transfer forces to stones below and around them. Each successive layer of stone spreads the load over a wider area. By the time forces reach the bottom of the ballast layer, they have spread across areas many times larger than the original contact area. This spreading effect reduces pressure on the underlying soil to levels it can safely support. The depth of the ballast layer, typically range from 25 to 30 centimeters, is calculated based on soil-bearing capacity and expected train loads using complex geotechnical formulas. Engineers use the Boussinesq equation and other stress distribution formulas to determine optimal ballast depth for specific conditions. Soil-bearing capacity testing involves taking core samples and conducting laboratory tests to measure how much pressure the soil can withstand. Train load calculations consider not just static weight, but also dynamic forces from acceleration, braking, and track irregularities. The formulas account for safety factors that ensure the ballast system can handle loads significantly higher than normal operating conditions. Advanced finite element analysis shows how load distribution efficiency depends on stone size gradation, with specific ratios of large to small stones optimizing the spreading effect. Computer modeling divides the ballast layer into thousands of small elements and calculates stress distribution to each element. These models reveal that uniform stone sizes create less effective load distribution than carefully graded mixtures. Large stones provide structural framework and resist major loads, while smaller stones fill gaps and improve contact between larger particles. The optimal gradation typically includes 60% large stones, 35% medium stones, and 5% small stones. This distribution maximizes load spreading while maintaining adequate drainage properties. The void spaces between stones rather than being. Wasted space actually contributes to load distribution by allowing stones to slightly rearrange under pressure. When trains apply loads, the ballast stones compress slightly and rearrange to better distribute forces. This rearrangement allows the stone matrix to adapt to changing load patterns and maintain optimal contact between particles. The void spaces also provide room for this movement without creating permanent deformation. Laboratory testing shows that ballast with proper void ratios can handle 30% higher loads than densely packed ballast with minimal void space. Dynamic loading from moving trains creates additional challenges as the ballast must distribute not just static weight but also impact forces. Moving trains generate impact forces when wheels encounter rail joints, switches, or track irregularities. These impact forces can exceed static loads by factors of 2 or 3. High-speed trains create additional dynamic effects from wheel-rail interaction at elevated speeds. The ballast system must absorb and distribute these dynamic forces without allowing permanent track displacement. Impact forces occur when train wheels encounter discontinuities in the track structure. Rail joints create vertical impacts as wheels transition from one rail section to another. Switch points generate both vertical and lateral impact forces as wheels change direction. Track irregularities from settlement or wear create additional impact loading. These impacts can generate force spikes reaching 40 to 50 tons per square meter instantaneously. The ballast system must distribute these extreme loads quickly enough to prevent damage to underlying structures. The stone matrix accomplishes this through rapid force transmission between interlocked particles. Without proper load distribution, the subgrade soil beneath ballast would fail, leading to track settlement, alignment problems, and potential derailment. Soil failure typically occurs through bearing capacity exceedance or excessive settlement. Bearing capacity failure happens when applied loads exceed the soil's ability to resist shear forces. This type of failure can occur suddenly and create dangerous track conditions. Excessive settlement develops gradually as soil compresses under repeated loading. Settlement creates track geometry problems that require expensive maintenance and can limit train speeds. This load distribution system represents one of the most effective and economical foundation technologies ever developed for heavy infrastructure. The ballast system handles loads comparable to those supported by concrete foundations at a fraction of the cost. Unlike concrete foundations, ballast systems can be easily modified, repaired, or relocated as operational requirements change. The granular nature of ballast provides inherent flexibility that accommodates thermal expansion, ground movement, and structural settlement. Yet distributing these massive loads is only part of what makes ballast stone so remarkable. The real engineering sophistication becomes apparent when you consider vibration control technology hidden in plain sight. Every train passage creates a complex symphony of vibrations that could destroy track infrastructure. Yet ballast stones operate as an invisible dampening system that most people never recognize. These vibrations originate from multiple sources during normal train operations. Wheels rolling over rail joints generate impact vibrations every few meters as trains travel. The continuous interaction between steel wheels and steel rails produces high-frequency vibrations throughout each journey. Engine vibrations from diesel locomotives or electric motors transmit through entire train consist into the track structure. Braking systems add additional vibrational loads when trains decelerate or stop. Even passenger movement inside train cars contributes to the overall vibration burden that track systems must absorb. The vibration control mechanism functions through energy dissipation, converting kinetic energy from train movement into heat via interparticle friction. This energy conversion occurs at thousands of contact points between individual ballast stones. When vibrations enter the ballast layer from above, they cause microscopic movements between stones. These tiny movements create friction at each contact point, and friction always converts kinetic energy into thermal energy. The heat generated dissipates immediately into the surrounding environment, but the cumulative effect of millions of these friction events absorbs substantial vibrational energy. The physics behind this energy dissipation involves multiple mechanisms operating simultaneously. Direct friction occurs when stones slide against each other under vibrational stress. Rolling friction develops when stones rotate slightly at their contact points. Deformation friction emerges when stones compress and decompress elastically under cyclic loading. Each mechanism contributes to overall energy absorption, though direct sliding friction typically provides the largest contribution. Engineers calculate expected energy dissipation using material properties and contact mechanics, allowing them to optimize ballast designs for specific operational requirements. High-speed rail systems operating at speeds exceeding 300 kilometers per hour create vibration frequencies that can resonate with track components and cause structural failure without proper dampening. These high-speed operations generate vibrations across wide frequency spectrums. Low-frequency vibrations, typically below 20 Hz, come from spacing between train cars and major track irregularities. Mid-frequency vibrations ranging from 20 to 200 Hz result from wheel-rail interaction and rail joint impacts. High-frequency vibrations above 200 Hz develop from surface roughness on wheels and rails. The most dangerous vibrations occur when their frequencies match natural resonant frequencies of track components. Resonance becomes particularly problematic because it amplifies vibration magnitudes far beyond normal levels. Rails have natural frequencies around 1000 Hz for vertical bending and 500 Hz for lateral movement. Sleepers typically resonate at frequencies between 100 and 300 Hz depending on their material and support conditions. When train-generated vibrations match these natural frequencies, resulting amplification can exceed safe stress levels in track components. The ballast layer must absorb these resonant vibrations before they build to destructive levels. The ballast layer functions like a mechanical filter, absorbing high-frequency vibrations while allowing tracks to remain stable under dynamic loading conditions. This filtering action works because ballast stones have natural frequencies much lower than problematic high-frequency vibrations from trains. High-frequency vibrations cannot propagate efficiently through granular ballast matrices because individual stones cannot respond quickly enough to transmit rapid oscillations. Instead, high-frequency energy gets absorbed through the friction mechanisms described earlier. Meanwhile, low-frequency movements necessary for proper load distribution can still pass through ballast systems. Research demonstrates that ballast can reduce track vibrations by up to 80% compared to direct track-to-ground contact, preventing fatigue damage to rail components. These research studies use accelerometers placed at various locations throughout track structures to measure vibration levels. Measurements taken on rail tops show full magnitudes of train-generated vibrations. Sensors placed within ballast layers show progressively lower vibration levels at greater depths. Measurements on subgrade soil beneath ballast typically show vibration reductions of 70% to 85% compared to rail-level measurements. The size and shape of ballast stones significantly affect their vibration-dampening properties, with angular stones providing superior energy dissipation compared to rounded alternatives. Angular stones create more contact points with neighboring stones, increasing total surface area available for friction-based energy dissipation. Rough surfaces of angular stones generate higher friction coefficients than smooth rounded surfaces. Sharp edges and corners on angular stones can deform slightly under load, creating additional energy absorption through elastic hysteresis. Laboratory testing confirms that angular ballast provides 40% to 60% better vibration dampening than rounded stones of identical material and size. Stone shape also affects how vibrations propagate through ballast matrices. Angular stones with interlocking surfaces tend to isolate vibrations within small local regions of ballast layers. Rounded stones allow vibrations to propagate more freely through materials because they have fewer mechanical connections with neighboring stones. This isolation effect means angular ballast not only absorbs more vibrational energy, but also prevents vibrations from spreading to areas where they might cause problems. Advanced monitoring systems now measure ballast vibration characteristics to predict when sections need maintenance or replacement before problems develop. These monitoring systems use networks of accelerometers embedded within ballast layers at strategic locations. Data collection systems record vibration measurements continuously and transmit information to central analysis facilities. Signal processing software analyzes data to identify changes in vibration patterns indicating ballast degradation. Machine learning algorithms can predict when vibration levels will exceed acceptable limits, allowing maintenance crews to schedule repairs proactively. Without adequate vibration control, railway tracks would experience accelerated wear, joint failures, and gradual loosening of all mechanical connections. Excessive vibrations create fatigue stress in rail fastening systems, causing bolts and clips to work loose over time. Rail joints experience accelerated wear when vibrations prevent proper load distribution across joint interfaces. Electronic signal systems can malfunction when subjected to excessive vibrations, creating potential safety hazards. This sophisticated vibration control technology represents just one aspect of ballast engineering that keeps modern railways operational. Yet even the most advanced vibration dampening becomes useless if another fundamental challenge isn't properly addressed: the drainage system that saves railways. Water poses one of the most serious threats to railway infrastructure. Yet ballast stones create an ingenious drainage system that operates invisibly beneath every train. Moisture threatens railway systems through multiple mechanisms that extend far beyond simple inconvenience. Standing water accelerates corrosion of steel rails, fasteners, and other metallic components throughout the track structure. Saturated soil beneath tracks loses its bearing capacity and can cause catastrophic settlement that destroys track geometry. Water infiltration into track components creates freeze-thaw damage in cold climates that can heave rails out of alignment. Electrical systems used for signaling and train detection malfunction when exposed to excessive moisture, creating potential safety hazards. The ballast drainage system prevents all these problems through carefully engineered water management that operates continuously without human intervention. The void spaces between ballast stones form an interconnected network of drainage channels that function at multiple scales throughout the ballast matrix. Large channels form between clusters of stones and provide primary drainage pathways for bulk water flow during heavy precipitation events. Medium channels develop between individual stones and handle normal rainfall drainage requirements. Small channels exist within the rough surfaces of individual stones and manage moisture absorption and evaporation processes. The interconnected nature of this channel network means that water can flow horizontally, vertically, or diagonally through the ballast layer depending on local conditions and drainage requirements. This channel network operates on principles similar to natural watershed systems, but with engineered precision. Water enters the ballast layer from above through precipitation, track washing operations, or groundwater seepage. Gravity pulls the water downward through vertical channels between stones, while slope gradients direct water horizontally toward drainage outlets along the sides of the track. The interconnected pathways ensure that water always has multiple routes to reach drainage outlets, preventing localized flooding even when some channels become temporarily blocked by debris or contamination. The drainage system must handle diverse water sources that create different challenges for track stability. Rainfall represents the most common water input, with intensities varying from light drizzle to heavy thunderstorms that can deliver extreme precipitation rates. Groundwater seepage occurs in areas where the water table intersects the ballast layer, creating sustained periods of water input that must be managed continuously. Spring snowmelt often occurs rapidly when temperatures rise, creating sudden surges of water input that can overwhelm inadequate drainage systems. Track cleaning operations use high-pressure water jets that introduce large volumes of water in concentrated areas that must be handled without disrupting train operations. Properly graded ballast drains far faster than natural soils, preventing dangerous water buildup that could compromise track stability. The high drainage capacity results from the optimal size distribution of ballast stones working together as an integrated system. Large stones create primary drainage channels that handle bulk water flow during peak conditions. Medium stones provide intermediate pathways that connect the large channels and ensure continuous flow throughout the system. The absence of fine particles ensures that small pores remain open for water movement rather than becoming clogged with sediment. The ballast layer incorporates carefully engineered slopes that direct water away from the track center line toward designated drainage outlets and collection systems. Cross-slope gradients typically range from 2% to 4%, creating positive drainage away from the rails under all conditions. Longitudinal slopes follow the natural terrain while maintaining minimum gradients that ensure water movement rather than ponding. Crown sections elevate the track centerline above the surrounding ballast to encourage lateral water flow toward drainage outlets. Contamination from fine particles can reduce drainage capacity by up to 90%, creating serious safety hazards that require immediate attention. Fine particle contamination occurs through multiple mechanisms that gradually degrade drainage performance over time. Wind-blown soil infiltrates the ballast layer and accumulates in void spaces between stones. Vegetation growth introduces organic matter that decomposes into fine particles that clog drainage channels. Coal dust and other cargo spillage creates contamination in freight railway corridors that can severely impact drainage effectiveness. The contamination process begins slowly but accelerates over time as fine particles create conditions that trap additional contamination. Initial contamination reduces void space and slows water flow through the ballast matrix. Slower water flow allows more fine particles to settle rather than being flushed away by normal drainage action. The accumulation process continues until drainage capacity becomes severely compromised. It requires intervention to restore proper function. In cold climates, effective drainage prevents freeze-thaw cycles that can leave trapped components and cause dangerous alignment problems. Water that remains in ballast void spaces during freezing weather expands by approximately 9% when it turns to ice, creating enormous pressures that can displace ballast stones and lift track components. Repeated freeze-thaw cycles gradually accumulate displacement that destroys track geometry and creates unsafe operating conditions. Proper drainage ensures that water flows away from the track before it can freeze and cause structural damage. Advanced drainage design incorporates geotextile fabrics beneath the ballast layer to prevent soil migration while maintaining water flow. These fabrics act as filters that allow water to pass while blocking fine soil particles that could contaminate the ballast system. The geotextile installation creates a permanent barrier that prevents contamination from below while preserving the drainage capacity of the ballast layer above. Railway maintenance crews use specialized equipment to test ballast drainage capacity and identify sections where cleaning or replacement is needed. Ballast cleaners and tampers are used to restore drainage and interlock properties every 10 to 20 years on busy lines, ensuring continued performance throughout the service life of the track structure. The sophisticated drainage system represents the difference between railways that operate reliably in all weather conditions and those that fail during storms or seasonal changes. Yet while this drainage technology appears universal, the materials that create these remarkable systems vary dramatically around the world based on local geological conditions and engineering requirements, global material variations, and their secrets. Different countries have developed distinct approaches to ballast materials that reflect both geological realities and engineering priorities shaped by local conditions. These regional variations demonstrate how engineers adapt universal performance requirements to work with available resources while maintaining safety standards. European railways often favor durable igneous rocks like granite and basalt, which offer superior resistance to wear and degradation despite requiring more energy-intensive processing. The geological history of Europe created abundant deposits of these crystalline rocks that formed deep within the earth under extreme heat and pressure. Granite quarries in Scotland, Norway, and Finland produce exceptionally hard ballast materials with mineral compositions that resist weathering for decades. These materials maintain their angular shapes through millions of loading cycles, making them ideal for high-traffic railway corridors where durability justifies higher initial costs. The process and requirements for these hard rocks reflect their superior performance characteristics. Crushing granite requires specialized equipment capable of handling materials that score 6 to 7 on the Mohs hardness scale. Primary crushers must apply enormous forces to fracture these crystalline structures, while secondary processing creates the angular shapes that European specifications demand. The higher energy consumption during production translates to ballast that lasts significantly longer than softer alternatives, reducing long-term maintenance expenses across railway networks. North American systems frequently employ limestone and dolomite ballast, which offers good performance characteristics while being more economically accessible across vast regions of the continent. The extensive sedimentary formations throughout central North America contain enormous limestone deposits that formed when ancient seas covered the continent. These carbonate rocks provide adequate hardness while being much easier to extract and process than igneous alternatives. Indiana limestone quarries produce millions of tons annually for railway applications throughout the Midwest, while Texas limestone formations supply southwestern rail networks. The economic advantages of limestone and dolomite extend beyond extraction costs to transportation expenses. Most North American population centers lie within reasonable distances of major limestone formations, reducing shipping costs that can represent significant portions of total ballast expenses. Limestone crushing requires less specialized equipment and consumes substantially less energy than granite processing. These economic factors make limestone ballast cost competitive despite requiring replacement more frequently than harder alternatives. Japan's high-speed rail network employs specially processed volcanic rocks selected for their exceptional drainage properties and ability to dampen vibrations crucial for smooth bullet train operation. Japan's volcanic geology created unique andesite and dacite formations with cellular structures that enhance performance characteristics essential for high-speed operations. These volcanic rocks contain natural porosity that improves drainage capacity compared to solid granite while providing superior vibration absorption through tiny air pockets within each stone that dissipate energy more effectively than solid crystalline materials. Processing techniques for Japanese volcanic ballast involve specialized methods that preserve beneficial cellular structure while creating optimal angular shapes. Temperature control crushing prevents thermal shock that could damage pore structure, while multi-stage screening removes weak particles while retaining stones with optimal void ratios. Quality control procedures test each production batch for porosity, drainage capacity, and vibration dampening characteristics specific to high-speed rail requirements. In Australia, where heavy haul mining railways transport immense loads, such as 200-car iron ore trains weighing over 20,000 tons, ultra-hard quartzite ballast is often used for its exceptional strength and ability to withstand extreme stresses. The Pilbara region contains quartzite formations with silica contents exceeding 95%, creating some of the hardest sedimentary rocks available. These formations approach the hardness of pure quartz, making them capable of handling axle loads that would crush softer materials within months of installation. Australian quartzite processing uses diamond-embedded crushing equipment designed specifically for ultra-hard materials. Primary crushing employs hydraulic breakers that fracture quartzite along natural crystalline boundaries, while secondary processing uses high-pressure techniques that create angular fragments without generating excessive fine particles. Mining companies accept higher initial costs because quartzite ballast reduces maintenance disruptions that could cost millions in lost production. Where high-quality stone is scarce or unavailable, engineers have developed alternative ballast materials including recycled concrete, steel slag, and synthetic aggregates. These alternatives offer sustainable approaches to ballast management, reducing waste and potentially lowering costs while their long-term performance characteristics remain subject to ongoing research and evaluation. Recycled concrete ballast uses demolished building materials processed to remove contaminants and achieve proper gradation. Steel slag ballast employs byproducts of steel manufacturing after treatment to remove harmful chemicals and adjust particle size distribution. Climate plays a significant role in ballast material selection, with tropical regions requiring ballast that resists chemical weathering caused by high humidity and temperature, which can degrade certain rock types. Railways in Southeast Asia use basaltic rocks with low porosity that resist water penetration and chemical attack. Arctic environments demand ballast materials specifically tested for freeze-thaw resistance and thermal expansion characteristics to prevent track instability in extreme cold conditions. Scandinavian railways employ granite varieties with uniform crystal structures that expand and contract consistently through seasonal temperature changes. The global ballast trade represents a significant industry involving the transportation of millions of tons of specialized stones across continents when local resources are insufficient or unsuitable. This international commerce moves premium materials from regions with optimal geology to areas building new railway systems or upgrading existing infrastructure. The economic and logistical aspects of this trade add complexity to ballast selection and management decisions. These diverse material strategies reveal how railway engineers worldwide solve identical fundamental challenges using whatever geological resources their environments provide. Yet all these carefully selected materials eventually face the same inevitable challenge that requires constant attention to maintain their performance. Maintenance secrets of the railway industry. Railway ballast requires sophisticated maintenance procedures that most travelers never see but are essential for safe train operation. These maintenance activities occur during scheduled track closures, often at night when passenger services stop running. Maintenance crews work under strict safety protocols because they operate heavy machinery near active railway corridors. The maintenance window typically lasts only 4 to 6 hours, requiring crews to complete complex operations efficiently. Track supervisors coordinate these activities to minimize disruption to train schedules while ensuring all safety requirements are met. Emergency maintenance procedures also exist for situations where ballast problems develop unexpectedly and require immediate attention to prevent service interruptions or safety hazards. Ballast cleaning operations use massive machines called ballast cleaners that excavate, screen, wash, and replace contaminated stones while trains continue operating on adjacent tracks. These machines weigh over 200 tons and operate on railway tracks using specialized bogies designed for heavy equipment. The cleaning process begins with excavation systems that dig beneath the sleepers to remove contaminated ballast down to the subgrade level. Conveyor systems transport the excavated material to screening equipment that separates reusable stones from fine contamination. Washing systems use high-pressure water jets to remove clay particles and other debris clinging to stone surfaces. Clean stones return to the track through distribution systems that place them precisely around the sleepers. The excavation process requires precise control to avoid damaging underground utilities and drainage systems. Operators use depth sensors and GPS guidance to ensure consistent excavation depths across the work area. The screening equipment includes multiple mesh sizes that separate stones into different categories based on their condition and contamination levels. Heavily contaminated stones go to waste disposal systems, while partially contaminated stones receive additional washing. The washing process uses recycled water systems that filter and reuse cleaning water to minimize environmental impact. Distribution systems include compaction equipment that ensures proper stone placement and density around the sleepers. The life cycle of ballast stones typically spans 15 to 30 years, depending on traffic density, climate conditions, and the quality of the original material. High-traffic freight corridors experience faster ballast degradation because heavy axle loads create more stone breakage and contamination. Passenger railways with lighter trains but higher frequencies still cause gradual ballast wear through repeated loading cycles. Climate factors affect ballast longevity through freeze-thaw cycles, chemical weathering, and moisture-related degradation. Premium ballast materials like granite and quartzite last longer than softer limestone or sandstone alternatives. Regular maintenance can extend ballast life by removing contamination before it reaches critical levels that require complete replacement. Contamination occurs gradually as ballast stones break down under repeated loading, creating fine particles that fill void spaces and reduce drainage capacity. This breakdown process accelerates when trains apply dynamic loads during acceleration, braking, and cornering. Stone-on-stone contact during train passage creates abrasion that generates fine particles over time. External contamination sources include wind-blown soil, vegetation growth, and spillage from cargo trains. Coal dust from the unit trains creates particularly problematic contamination because it forms cohesive mixtures with water that severely reduce drainage. The contamination accumulation follows predictable patterns that maintenance engineers monitor to schedule cleaning operations. Modern maintenance strategies use ground-penetrating radar and other technologies to assess ballast condition beneath the surface without excavation. Ground-penetrating radar systems emit electromagnetic pulses that penetrate the ballast layer and reflect off interfaces between clean ballast, contaminated areas, and the subgrade soil. Signal analysis software interprets these reflections to create detailed maps showing contamination distribution throughout the ballast depth. This technology allows maintenance crews to identify problem areas before they affect train operations and helps railroads reduce costs substantially because they avoid spending resources on areas that don't require remediation. Ballast shoulder maintenance involves reshaping and compacting the stone slopes alongside tracks to maintain proper drainage and prevent lateral track movement. Shoulder maintenance equipment uses adjustable mold boards to reshape ballast slopes to specify profiles. Compaction systems ensure adequate stone density in shoulder areas that provide lateral track support. Proper shoulder geometry directs water away from the track center line toward drainage ditches and collection systems. Inadequate shoulder maintenance allows water to pond near the rails, accelerating corrosion and creating safety hazards. Specialized tamping machines compact and align ballast stones around sleepers, using synchronized vibrating tools that optimize stone positioning. Tamping machines use hydraulic systems to insert vibrating tools beneath each sleeper simultaneously. The vibrating action rearranges ballast stones into optimal positions that provide maximum support and load distribution. Computerized control systems ensure consistent tamping pressure and vibration patterns across all sleeper positions. Modern tamping machines include laser guidance systems that maintain precise track geometry during the compaction process. Predictive maintenance programs analyze ballast degradation patterns to schedule cleaning and replacement operations before safety issues develop. These programs use databases containing historical maintenance records, traffic loadings, and environmental conditions for each track section. Statistical analysis identifies correlations between operating conditions and ballast degradation rates. Machine learning algorithms process this data to predict when specific sections will require maintenance attention. The predictive models consider factors like train speeds, axle loads, weather patterns, and previous maintenance history. The economics of ballast maintenance involve balancing the cost of cleaning versus complete replacement, with decisions based on contamination levels and remaining stone life. Transportation costs often exceed material costs for ballast, making quarry location relative to railway projects a critical economic consideration. Research from ballast and foundation materials programs shows that transport and purchase price dominate ballast cost decisions. Quality versus cost trade-offs require engineers to balance initial ballast expenses against long-term maintenance costs and service life expectations. These maintenance secrets reveal why railway systems can operate safely for decades while handling millions of tons of cargo and passengers annually. The sophisticated maintenance procedures represent accumulated knowledge from over 150 years of railway engineering experience. Modern technology enhances traditional maintenance methods while reducing costs and improving safety outcomes. Yet as these massive maintenance operations continue worldwide, the industry faces growing pressure to address the broader implications of ballast production. Quarrying operations for ballast production significantly impact local ecosystems, requiring careful environmental management and restoration planning throughout the extraction process. Large-scale quarries remove entire hillsides and disturb underground water systems that support surrounding vegetation and wildlife communities. The extraction process strips away topsoil that developed over centuries, eliminating habitat for countless organisms that depend on these established ecosystems. Blasting operations fragment remaining habitat areas and create noise pollution that disrupts wildlife behavior patterns and migration routes. Dust from crushing operations settles on nearby vegetation, reducing photosynthesis efficiency and harming plant communities that form the foundation of local food webs. Heavy machinery compacts soil around quarry sites, preventing natural regeneration of native species and creating long-term ecological damage. Water runoff from quarries carries sediment and chemical residues into nearby streams and rivers, affecting aquatic ecosystems downstream. Environmental management at quarry sites now includes detailed impact assessments before operations begin to identify and protect sensitive ecological areas. These assessments identify endangered species and critical habitats that require protection during extraction activities, ensuring compliance with environmental regulations. Quarry operators develop comprehensive restoration plans that specify how sites will be rehabilitated after stone extraction ends, often creating new ecological opportunities. Progressive restoration allows portions of quarries to be rehabilitated while other areas remain active, minimizing the total disturbed area at any given time. Native seed banks are preserved and used to restore indigenous plant communities that support local wildlife populations. Artificial wetlands treat quarry runoff before it enters natural water systems, removing contaminants and sediments. Wildlife corridors connect fragmented habitats around quarry boundaries, allowing animals to move safely between remaining natural areas. Transportation of ballast materials often involves long-distance trucking or shipping, contributing to carbon emissions that railways are working to reduce through improved logistics and route optimization. Many railway projects cannot source suitable ballast locally, requiring transportation across hundreds or thousands of kilometers to reach construction sites. Premium granite from Scandinavian quarries travels to construction sites throughout Europe and beyond, while Australian quartzite ships to North American mining railways for heavy haul applications. These transportation networks generate substantial carbon emissions that offset some environmental benefits of rail transport compared to other freight modes. A single ballast shipment can involve 50 to 100 truckloads, each consuming diesel fuel and producing exhaust emissions during transport. International shipping of ballast uses heavy cargo vessels that burn marine fuel oil with high sulfur content, contributing to air pollution and greenhouse gas emissions. Railways are implementing transportation optimization strategies to reduce these emissions while maintaining access to quality materials. Regional sourcing policies prioritize local materials even when they require more frequent replacement, reducing transportation distances and associated emissions. Improved logistics coordinate ballast deliveries to minimize empty return trips and optimize vehicle utilization rates. Multimodal transportation combines rail and truck transport to reduce road miles and take advantage of rail's superior fuel efficiency. Some railways invest directly in quarries near major maintenance facilities to minimize long-distance transportation requirements. Electric vehicles are beginning to replace diesel trucks for short-distance ballast transportation in urban areas. Rail transport of ballast from quarries to construction sites reduces carbon emissions compared to exclusive truck transport over long distances. Recycling programs now recover and process used ballast, removing contamination and returning clean stones to service rather than disposing of them in landfills. Traditional ballast disposal involved hauling contaminated material to waste sites. Modern recycling programs use mobile processing equipment that travels to work sites and cleans ballast on location, reducing transportation costs and environmental impact. The cleaning process separates reusable stones from fine contamination through screening and washing operations that restore original specifications. Recovered stones undergo quality testing to verify they meet original specifications for strength and durability before returning to service. Recycling typically recovers 70% to 85% of original ballast volume while reducing new material requirements by the same percentage, significantly reducing quarrying demands. Advanced recycling technologies continue improving recovery rates and stone quality through specialized processing techniques. Density separation removes lightweight contaminants like vegetation and plastic debris that accumulate during service. Magnetic separation extracts metal fragments from ballast contaminated by rail wear and maintenance activities. Chemical washing removes oil and grease contamination from ballast in industrial areas where cargo spillage occurs. Thermal treatment can remove organic contamination that resists conventional washing methods. The recycled ballast often performs as well as new material while costing 30% to 50% less than virgin stone, creating economic incentives for sustainable practices. Research into alternative materials focuses on using industrial byproducts like steel slag and recycled concrete as ballast substitutes to reduce quarrying demands. Steel slag from metal production has similar hardness and angularity characteristics to natural stone after proper processing. Processing removes harmful chemicals and adjusts particle size distribution to match ballast specifications for railway applications. Recycled concrete from demolished buildings provides another ballast alternative after crushing to appropriate sizes and cleaning to remove reinforcing steel and other contaminants. GeoGrid reinforcement systems are being tested to enhance ballast performance and extend service life. Polymer-coated stones undergo durability testing to determine whether surface treatments can improve resistance to wear and contamination. Life cycle assessments compare the environmental impact of different ballast materials and maintenance strategies to identify the most sustainable options for specific applications. These assessments quantify energy consumption, carbon emissions, water usage, and waste generation throughout the entire ballast life cycle from extraction to disposal. Natural stone quarrying typically has high initial environmental impact, but provides long service life that amortizes the impact over decades. Recycled materials have lower initial impact, but may require replacement more frequently, affecting total life cycle impact. Transportation represents a significant portion of total environmental impact for most ballast options, making local sourcing increasingly important. Maintenance strategies affect life cycle impact through cleaning frequency and replacement intervals that determine total resource consumption. Water management at quarry sites addresses concerns about groundwater impact and sediment control during ballast washing operations. Quarry dewatering can lower groundwater levels in surrounding areas, affecting wells and natural springs that communities depend on. Sediment from washing operations can clog streams and harm aquatic ecosystems if not properly controlled through engineering measures. Modern quarries use closed-loop water systems that recycle washing water and prevent contaminated discharge into natural water bodies. Settling ponds allow suspended sediment to precipitate before water returns to natural systems, protecting downstream water quality. Groundwater monitoring ensures that quarry operations do not adversely affect local water resources that support both human communities and natural ecosystems. Biodiversity conservation efforts work to minimize quarrying impact on wildlife habitats and restore quarried areas for ecological use after extraction ends. These sustainability initiatives demonstrate how the railway industry is evolving to balance infrastructure needs with environmental responsibility through comprehensive planning. The development of innovative ballast materials, including recycled plastic composites and other sustainable alternatives, continues advancing as environmental pressures increase and traditional resources become less accessible. These environmental considerations increasingly influence the complex economic calculations that drive ballast selection and procurement decisions worldwide. Economic forces behind the stone industry. The scale of financial activity within ballast procurement reveals why this seemingly simple material drives complex economic decisions across the global railway industry. Transportation costs often exceed material costs for ballast, making quarry location relative to railway projects a critical economic consideration. The expense of moving thousands of tons of stone across hundreds of kilometers can double or triple the delivered price compared to quarry gate prices. Railways must factor these transportation expenses into their project economics, sometimes choosing inferior local materials over superior distant alternatives, purely for cost reasons. The transportation challenge becomes even more complex for island locations or landlocked regions where multiple transportation modes increase handling costs and delivery times. Quality versus cost trade-offs require engineers to balance initial ballast expenses against long-term maintenance costs and service life expectations. Premium granite ballast might cost significantly more per ton, delivered while acceptable limestone alternatives cost substantially less, creating pressure to choose cheaper options. However, the superior durability of granite extends service life considerably, fundamentally changing the economic calculation. Engineering analysis must consider maintenance frequencies, track closure costs, and equipment mobilization expenses that occur repeatedly with inferior materials. The hidden costs of frequent maintenance often exceed the initial savings from cheaper ballast, making quality materials the economically rational choice despite higher upfront expenses. Regional pricing variations can be extreme, with ballast costs differing by 300 to 500% between areas with abundant local stone and regions requiring long-distance transport. Quarry gate prices in stone-rich regions might be relatively modest for premium granite, while the same material to ballast-poor regions can cost several times more after transportation and handling charges. These dramatic price differences create economic incentives for long-distance ballast trade, with specialized shipping operations moving millions of tons annually between continents. Regional price disparities also influence railway development strategies, encouraging concentrated construction in areas with favorable ballast economics while discouraging expansion in high-cost regions. Large infrastructure projects like high-speed rail lines can consume millions of tons of ballast, creating temporary market demand spikes that affect pricing globally. Major railway construction projects represent more than the annual production capacity of many regional quarries, creating boom and bust cycles in ballast markets with prices spiking during construction phases and decline when projects complete. Quarry operators must carefully manage capacity expansion to avoid overinvestment during temporary demand surges. These megaprojects strain global supply chains and require careful coordination between multiple suppliers to meet delivery schedules. Long-term supply contracts between railways and quarries help stabilize pricing but require accurate forecasting of maintenance and expansion needs. These contracts typically span multiple years and involve substantial tonnages of material, creating significant financial commitments for both parties. Railways benefit from price certainty that enables accurate budgeting and project planning, while quarries gain revenue stability that justifies equipment investments and capacity expansion. However, contract negotiations must account for inflation, fuel cost fluctuations, and changing regulatory requirements that affect production costs. Force majeure clauses protect both parties from unforeseeable events like natural disasters or economic disruptions that could affect contract performance. Economic analysis includes hidden costs like track downtime during ballast replacement, which can exceed the material cost for busy railway corridors. High-traffic passenger lines generate substantial revenue per hour, making maintenance windows extremely expensive. Freight corridors carrying coal or containers can lose significant revenue for each day of track closure. These opportunity costs often dwarf the actual ballast replacement expenses, creating powerful incentives for maintenance strategies that minimize service disruptions. Railways increasingly invest in premium ballast materials and advanced maintenance equipment that reduce closure frequencies and duration, improving overall economic performance despite higher initial costs. International trade in specialized ballast materials creates opportunities for developing countries with suitable geology to export to major railway markets. Countries with abundant high-quality stone deposits have developed substantial ballast export industries serving global markets. These exports generate foreign currency earnings while supporting local employment in quarrying and transportation sectors. However, developing countries must balance export opportunities against domestic railway development needs, ensuring adequate supplies remain available for local infrastructure projects. Environmental concerns about quarrying operations also create tensions between economic opportunities and conservation objectives that governments must carefully manage. Technology investments in ballast production and maintenance equipment require substantial capital but can reduce long-term operational costs significantly. Modern ballast cleaning machines represent major capital investments but can process thousands of tons per hour with minimal labor requirements. Automated quarry operations reduce production costs, while improving safety and environmental performance. Advanced materials testing equipment ensures consistent quality that reduces maintenance requirements and extends service life. These technology investments often pay for themselves within reasonable timeframes through improved efficiency and reduced operating costs. Railway financing institutions now recognize ballast economics as a critical factor in project viability assessments. Development banks require detailed ballast cost analyses before approving railway loans, understanding that material costs can determine project success or failure. Private investors conducting due diligence on railway acquisitions examine ballast condition and replacement schedules as key value drivers. Insurance companies assess ballast quality when setting premiums for railway property coverage, recognizing that inferior materials increase derailment risks and claim frequencies. These economic forces demonstrate why ballast selection involves complex financial calculations that extend far beyond the simple cost per ton of stone. The total cost of ownership includes material procurement, transportation, installation, maintenance, and opportunity costs from service disruptions. Sophisticated economic modeling considers all these factors over the entire asset lifecycle, typically spanning decades for railway infrastructure. Yet as these economic pressures continue shaping traditional ballast markets, emerging technologies promise to transform how railways approach these fundamental engineering challenges. Future technologies transforming railway foundations. Revolutionary technologies are emerging that could transform how railways approach track foundation systems and ballast management. Research laboratories across the globe are developing innovations that address fundamental limitations of traditional stone-based systems. These technological advances promise to revolutionize railway maintenance practices, extend infrastructure lifespans, and reduce operational costs. The convergence of materials science, sensor technology, and artificial intelligence creates unprecedented opportunities to reimagine how railways support the enormous loads and stresses of modern train operations. Smart ballast systems incorporate sensors that monitor load distribution, vibration levels, and moisture content in real time to optimize maintenance scheduling. These sensor networks use wireless communication protocols to transmit data continuously from thousands of monitoring points throughout the ballast layer. Each sensor measures multiple parameters, including pressure variations, temperature fluctuations, and water content changes that indicate ballast condition. The monitoring systems detect early warning signs of ballast degradation before problems become visible through conventional inspection methods. Advanced algorithms process the sensor data to identify patterns that predict when specific track sections will require maintenance attention. The sensor technology includes strain gauges embedded within individual ballast stones to measure internal stress distributions. Accelerometers detect vibration patterns that indicate loose ballast or inadequate compaction. Moisture sensors identify drainage problems that could lead to ballast contamination. Temperature sensors monitor freeze-thaw cycles that affect ballast stability in cold climates. The wireless transmission systems operate on low-power protocols that enable sensors to function for years without battery replacement. Polymer-modified ballast uses chemical treatments to improve stone durability and reduce degradation rates, potentially doubling service life. Chemical engineers have developed polymer coatings that penetrate the surface layers of ballast stones and create protective barriers against weathering. These treatments reduce the formation of fine particles that contaminate ballast systems and impair drainage performance. Laboratory testing shows that polymer-treated stones maintain their angular shapes through millions of loading cycles, while untreated stones gradually round and lose their interlocking properties. The polymer modifications also improve resistance to chemical weathering from acid rain and salt exposure in coastal environments. Different polymer formulations target specific degradation mechanisms that affect ballast performance. Silane-based treatments create hydrophobic surfaces that repel water and prevent freeze-thaw damage. Epoxy coatings provide mechanical protection against abrasion and impact forces. Polyurethane modifications enhance flexibility and reduce brittle fracture under dynamic loading. The application process involves vacuum impregnation techniques that ensure uniform polymer distribution throughout the stone structure. Geosynthetic reinforcement systems combine traditional ballast with advanced fabrics and grids that enhance load distribution and reduce settlement. These reinforcement materials use high-strength synthetic fibers woven into precise geometric patterns that optimize force transmission through the ballast layer. The geosynthetic grids interlock with ballast stones to create composite structures with superior mechanical properties compared to unreinforced systems. Installation involves placing reinforcement layers at specific depths within the ballast profile to maximize load spreading benefits. The synthetic materials resist chemical degradation and maintain their properties throughout the design life of the railway infrastructure. Advanced geosynthetic designs incorporate biaxial grids that provide equal strength in perpendicular directions. Triaxial configurations offer enhanced stability for curved track sections where lateral forces are significant. The aperture sizes in these grids are precisely calculated to achieve optimal stone interlocking while allowing proper drainage. Some systems include geotextile separation layers that prevent soil migration into the ballast while maintaining water flow. Artificial intelligence analyzes ballast performance data to predict maintenance needs and optimize replacement strategies across entire railway networks. Machine learning algorithms process vast datasets containing historical maintenance records, traffic loadings, weather patterns, and inspection results to identify factors that influence ballast degradation rates. These predictive models can forecast when specific track sections will require attention with accuracy exceeding 90%. The AI systems continuously learn from new data and refine their predictions as more information becomes available. Railway operators use these predictions to optimize maintenance schedules, allocate resources efficiently, and minimize service disruptions. The AI applications extend beyond simple prediction to optimization of maintenance strategies across complex railway networks. Algorithms consider factors like crew availability, equipment scheduling, material supply chains, and traffic patterns to recommend optimal timing for ballast work. The systems can simulate different maintenance scenarios to identify strategies that minimize total lifecycle costs while maintaining safety standards. 3D printing technology is being explored for creating synthetic ballast with optimized shapes and properties that exceed natural stone performance. Additive manufacturing processes can produce ballast particles with complex internal structures that enhance strength-to-weight ratios and drainage characteristics. The printing materials include high-performance ceramics and polymer composites designed specifically for railway applications. Computer modeling optimizes particle shapes to maximize interlocking properties while maintaining adequate void spaces for drainage. The manufacturing process enables quality control that ensures every particle meets exact specifications, eliminating the variability inherent in natural stone materials. Recycling innovations use advanced separation techniques to recover and reprocess ballast with near-original quality specifications. These systems employ optical sorting, density separation, and chemical cleaning processes to remove contamination and restore ballast properties. Automated maintenance systems could deploy robotic equipment for ballast cleaning and replacement without requiring track closures. These emerging technologies suggest that railway foundations may evolve significantly from current stone-based systems, yet the fundamental engineering principles they address remain constant. Whether through smart sensors, advanced materials, or automated systems, the goal remains the same: creating stable, durable foundations that safely support the massive forces of modern rail transport. The innovations represent evolutionary improvements rather than complete departures from established engineering wisdom that has proven itself over more than a century of railway operations. These technological advances point toward a future where railway foundations become increasingly sophisticated while maintaining their essential purpose. The next time you see those carefully placed stones along railway tracks, you'll understand that you're looking at one of engineering's most elegantly simple yet sophisticated solutions. These billions of precisely engineered stones represent the foundation of a transportation system that moves trillions of dollars in goods and millions of passengers safely every year. The global railway market surpassed 200 billion euros in 2024, highlighting the enormous scale supported by these seemingly ordinary rocks. The hidden complexity behind something so seemingly ordinary reveals how much engineering genius surrounds us in plain sight, waiting to be discovered and appreciated.